Let's look in depth at the DC motor example. So you might remember that this DC motor is controlled through a field current. So IF stands for the field current, and we have some resistor here, some inductor here, and we can make that field current change its value by changing V sub F. So V sub F, or the field voltage, that's the knob that we can turn, that's our input to the system. And as we change that current, it actually turns a motor. So the motor looks a little bit like this. We're going to zoom in on it in a second and look a little bit more. And in order to make the motor turn, we have an armature, inductor, and resistor, and that induces an armature current. So if we zoom in on the motor, we can see that we actually have a few different kinds of dynamics here. So there's the dynamics of the motor. The motor has its own dynamics, that is, the way it behaves with respect to time depending on its inputs. We also have load dynamics. So as the motor turns, it moves the load around, and usually that load doesn't like to be moved because of Newton's laws of rotational motion, so we'll look at that in a minute too. And we also have some disturbances. So this is somebody bumping up against it or reaching out with their hand or maybe trying to spin it a little bit faster. So we don't know what the disturbances are necessarily going to be doing, but it doesn't fit into the strict dynamics of the load, and it doesn't come directly from the motor dynamics that are our inputs. So it's just some extra torques that get added in there. We don't really have any control over how it happens. So we indicate the motor dynamics, or Tm, that's the torque due to the motor. So if you want to think about it as turning left in the same way in the same direction that theta is turning here, or counterclockwise. And then we have the load dynamics, T sub L, so that's the torque due to the load. So that's opposite of the motor torque, so it's in the clockwise direction. And we're also assuming that the motor disturbance is in the clockwise direction. So the next step is to remember that the sum of all the torques is the rotational moment of inertia times the angular acceleration, or I is equal to theta double dot. So the motor torque, again, Tm, the load torque, TL, and the disturbance torque, T sub D. So we want to try to identify, for these three torques, mathematically, what do they mean? So when we're specifying the motor torque, we can actually take a small aside here and see that motor torque is actually a function of some constant K1 times phi times the armature current I sub A. So phi is actually the air gap flux. So this is where when we input our field current I sub F, it gets multiplied by some gain and produces a flux air gap. So if you've ever had a class on transformers, for example, this flux induces another current in another circuit. So we're making the current flow by changing the knob V sub F, and that's going to induce a current on the other side through phi, through the air gap flux, that's going to turn into a torque. So with a little bit of extra derivation that comes from DC motor design, it's not really covered in this class, but I like to talk about where these equations come from. Typically what you do is you actually keep I sub A of t instead of a time-varying signal. You actually make that a constant current. So you just turn on that current. And then when you do that, you can actually reduce your, so this motor constant K sub M reduces away from all these time-varying functions and other multipliers, etc. You can just say, I've got K sub M, which represents the gain multiplier for my input field current I sub F, is going to produce a torque for me. So those are all based on those kinds of physical values. So then we next have the load torque. So the load torque is based on the moment of inertia, J, and the friction, B. So the load torque is equal to J times theta double dot, because the moment of inertia is for the second moment, and B theta dot, because theta dot is a frictional force, so it's related to the velocity and not position. That is, the faster you move, the more likely it is to try to resist it. So again, these two sort of resistances add up for T sub L, right? They're both in the same direction. So if we look carefully at the motor again, for how all these pieces are going to fit together, we have theta turning in this direction. The motor torque is applied counterclockwise. And then the load torque resists in two ways. So it resists in one way through inertia. That is, when you push on it, you try to get it to start moving, so this is the second derivative, you try to accelerate it, and then it resists that acceleration through inertia, but it also resists your velocity through friction. So those are the two resistances. And then for the disturbance torque, again, this is just some value that's showing up. We don't have any control over it. Could be positive, could be negative. So we can add these three things together. If you think of the sum of all torques as equal to the moment of inertia times theta double dot, so we have the sum of all torques is equal to Tm, so that's Km times If. We recall that that's equal to Tm over there. And then the sum of all the moments of inertia and other losses are J theta double dot plus B theta dot. And normally we would add TD on the left-hand side, but I've gone ahead and put it on the other side so I can isolate all my theta terms. You'll see why I did that in a minute. So let's write this up at the top so that we have a place where we can keep it. Okay, so this is my first equation. And now I'd actually like to try to relate the torque of the motor to the input voltage. And I can actually do that with Kirchhoff's voltage law. So V sub F, if we go back to the fundamental dynamics of circuits, is my inductor LF times the rate of change of the current, dIF dt, plus the resistance RF times IF. So we've just done a sum in that loop. VF is equal to RF IF times LF dIF dt. So these are our two equations. We have one that relates the field voltage V sub F that we can potentially find out what I sub F is equal to, and then another one that relates theta to I sub F. So I'm going to try to take the Laplace transform of each of these objects, each of these equations. So if I take the Laplace transform of equation 2, VF is equal to LF times S IF. Because again, we have the derivative here, so to take the derivative of something, we multiply it by S in the Laplace domain, plus RF times IF of S. And likewise, for the second, we're going to have J times S squared theta plus B S theta is equal to Km times IF of S minus TD of S. So again, we're assuming that TD could be a time-varying function here, so we're going to have that be TD as a function of S in the Laplace domain. So let's do a little bit of simplification of these functions. So we're going to start with them exactly as they were on the previous page. And now I'm going to try to isolate IF of S over on one side. So my field current, IF, is equal to the field voltage divided by LF times S plus RF. So the transfer function, as you remember, is the output divided by the input. So, for example, theta S over VF of S is going to be a transfer function we're going to try to find. I want to be able to relate the angle of the motor to my field voltage. So, I'm going to go ahead and, in this top example, I'm going to actually try to put, or try to divide through by LFS plus RF, and assume that TD of S is going to be equal to 0. So I've gone ahead and substituted that IF is equal to VF divided by LF times RF, LFS plus RF. So I've taken, I've taken this equation here and plugged it in to the IF that's right there. And I'm going to assume that the disturbance is equal to 0 for now. So now I'm going to rewrite the left-hand side of this equation by factoring out the theta and giving myself JS squared plus BS is equal to KMVF divided by LFS plus RF. So again, I've just taken this and moved it down and factored out the theta of S on the left-hand side. So I can divide through by VF and get that theta of S is equal to our motor constant Km divided by these two dynamical pieces. So there's JS squared plus BS, that's the piece that's related to the motor, and then multiplied by LFS plus RF. That's the piece that's related to our input circuit. So you can see that in the Laplace domain we're able to separate these two pieces out. And we're going to draw a block diagram in a minute that exemplifies this even more. So this gives us our transfer function G of S. So G of S relates the motor constant and its various and the various inputs that you get with the motor constant, the various pieces that you have there. So what I've done is I've divided by J and divided by LF so that we can isolate the S squared terms and the S by themselves. So you can see that we have on the top it's the motor constant divided by the moment of inertia times the inductor, and then in the denominator we have one integrator, that's the 1 over S. And then we have a transfer function that relates the motor constant and inertia, and then another transfer function that relates the resistor and the inductor from the field input. So let's just let tau sub f be some time constant for the field circuit, and tau sub l be some time constant for the motor, the actual dynamics of the motor. So now we can write this as t sub m s plus 1, that is the portion of our transfer function relating to the motor, times t sub l s plus 1, so that's the portion of the transfer function related to the, the t sub, should be t sub f, not t sub l of s there. Okay, so now let's look at this as a block diagram. So I'm going to lay these out. So we have our first input voltage, V sub f, and so this is the field part of our transfer function. So V sub f is transformed into I sub f of s according to this transfer function. That is, this is a little bit of a delay we get from the inductor and the resistor. So we multiply this by the motor constant. IF times the motor constant gives us the torque that shows up in the motor. And then we're going to subtract away the disturbance from the torque, and that's going to give us the load torque. That is the torque that's actually being applied to the load. And then the load dynamics will affect that load torque to give us the actual angular velocity. And then we'll integrate that angular velocity in order to get the angle itself. So this is the block diagram that decomposes all those other pieces. And it's based partially just on the structure of the transfer function and partly based on the physical system that we wrote down. So I'm going to define that y of s is equal to omega of s. That is, the output that I'm interested in is the angular velocity, not the actual angle. And by the way, theta of s is equal to y of s over s. So s times theta of s is equal to y of s. So this gives you that y of t is equal to d delta dt. That is, my y output is the time rate of change of theta. So just for giggles, I'm going to let this transfer function, for example, g sub td, I'm going to let this be the disturbance transfer function, and I'm just going to express this as some ratio b over a. And I'm going to have some other transfer function, a over tau 1 s plus 1, tau 2 s plus 1. So I've got this plant, and then I've got a disturbance, and I want to see how my input is going to be affected based on whether or not I'm getting inputs from the disturbance or getting inputs from something that I can control. So this gives us our open loop dynamic behavior. So here we have Td, which goes into G sub Td. So that's our disturbance torque. And then we have an input field voltage. And then we pass all of these through the transfer function G sub f. So here's a question. What's the response of y of t to some step change of minus 0.1 Newton meters? That is, again, we're just basically rewriting this behavior. It's not an exact analog to the previous system, right? We're just saying I'm going to rewrite the system looking like this. So I know that I'm actually sort of pre-multiplying some of the dynamics of the disturbance torque so that I can add them directly to the field voltage, and then dividing those back out. So somebody's going to produce a disturbance, a step input, to T sub D, and we're going to try to basically mess up the motor. So I want to say, well, how much is the motor actually going to be messed up if they do this? So in the closed loop dynamic behavior, we have a different way to look at this. Now we have a controller, and that controller produces the field voltage. So now if somebody produces T sub D, which is a disturbance torque again, and that goes through the disturbance torque transfer function, we can use a controller to try to reject that disturbance. So in this particular setup, we can ask the same question. What's the response of y of t to a step input of disturbance torque of minus 0.1 Newton meters. So the difference in between these two examples, I'm going to back up so you can see the other one. Here we have just an input disturbance torque, and we've chosen the knob value ourselves for V sub f. And so we've selected that we want V sub f to be, I don't know, 10 volts. And every time somebody inputs a disturbance torque, we're going to get a different y of t response. And in this example too, we've now provided a reference value, and that reference value is going to be, for example, how fast we want the motor to be turning. And we have a controller that turns our idea of motor angular velocity into an input voltage. So we're letting the controller decide on the voltage depending on how fast it's actually going. So here, the disturbance might come in, somebody might turn on a switch and try to make the motor slow down, but if it slows down too much, our controller is going to try to overcome that. And so in this different structure, we can also ask, again, the same question. If somebody provides an input torque of a certain value, how will y change? So the solution to this is that we'll use the Laplace transform and the inverse Laplace transform on the transfer functions that we have of this system. So we'll begin by transforming the equations of motion into the Laplace domain. Then we'll apply whatever that input happens to be, or the disturbance happens to be, in the Laplace domain using some algebraic technique. So that's going to get us our output y of s. And then we'll take the inverse Laplace transform in order to calculate y of t. So this is the general approach that we'll be doing in order to figure out what the time response of a system will be, either to a step input or to a step disturbance.